Okay, so we'll make a start. Thank you very much, everybody, for joining this session on systems. So this is our breakout session, second breakout session of the afternoon. Very much looking forward to interacting with you and sharing your views around the exciting world of systems. So systems, as we all know, is quite a diverse particular area of interest. It covers many, many different things. The area that we've just had a breakout session in this room on propulsion and power, which is some very large complex systems, another aspect of systems. We're going to dive into all of the rest of the systems that are on the aeroplane and start to touch on some of the considerations specifically brought out in our strategy. And when we're thinking about systems, one sort of calibration point, everybody thinks about devices like your little phone and things like that. So this is systems technology, isn't it? So our friends Apple, who developed this wonderful technology, they spend more than $16 billion a year on R&D for that. And how many updates do you get in terms of software and all that kind of good stuff? So it doesn't really matter how much money you put into this, it's about how focused you are in what you want to deliver. So that's just a little bit of a calibration point. So on the world of systems, so today's session, hopefully you've just been to another panel session somewhere else, you've seen the format. So what we're going to do, I'm going to give you a 15-minute pitch around expanding on the strategy that Simon talked about this morning, specifically for the systems area. Then each of our panelists will then talk about, for 5 minutes each, they'll talk about their particular aspect, their view, their context for one area each of the strategy. And then we'll really dive into your questions. And we've got the Slido app, so big opportunity for you to share your view, your questions, and really interact with us and make it a vibrant discussion. So there's the code. If you don't already have it and you've not logged in already, this is the code. You're in the systems room, so get ready for your questions. So, first of all, in terms of the world of systems, so we're going to, initially we'll talk about targets and drivers. So what are the targets and drivers for systems? So our first one that we've got in there is about size, weight, power, and cost. So it's a multiple target, a hybrid target with lots of things. But we all know that the cost of systems on aircraft has to decrease. To make it commercially viable, we have to make some significant impact in terms of cost. We know there's going to be more systems, hence the need for reducing the cost of systems. We need to reduce the amount of power that's being consumed by those systems to make all of the rest of the aeroplane viable as well. We need to think about the weight of those systems, so we need to think about power densities and all of those things. So we've got some quite significant reductions that we're looking for in terms of our systems and going forward. Our next one is really about the time it takes to actually get our technology from a concept through to EIS. And we know that today it can take several years. Actually, that several years, it's in some cases, is driven by almost airframe requirements not being created in time to actually develop some of these systems. But in reality, that's a bit of an excuse, isn't it? We all know that. There's absolute perfect sense in actually trying to drive improvements in terms of the iteration time it takes to develop some of these systems of the future. So if we can then put in more and more capability, deliver more upgrade capability, there's even more market opportunity and commercial opportunity for systems providers, even beyond what we do today. So great opportunities around time to market. And then our drivers are drivers that you should be familiar with if you're used to talking to the ATI. So very much about continuing to improve safety, certainly around the world of costs. So I've mentioned cost, all sorts of different costs that you can think about. So the cost of the equipment, the cost of actually maintaining and operating the equipment, and many other aspects of cost as well. Improving energy efficiency. So that big reduction in power utilization for the systems is a big deal. So could we do more in terms of reducing our demands from equipment on the aeroplane by having more intelligent systems? Could we find ways to actually redistribute loads on the aircraft to actually improve energy efficiency? Protecting the environment is clearly an important factor, fits very nicely with what we've been talking about already. we certainly want to think about all of aspects of systems that can help to benefit on the environment. We're going to add lots more systems in the future. So all of the concepts that we have been talking about and will continue to talk about drive the need for more and more systems. And we all know what that means. That could mean complexity. It could mean all sorts of things that, from an engineering perspective, really don't make sense. So we need to find ways of keeping our systems simple, viable, operational, and successful. So how can we do that? We need to be thinking about really driving how we can effect quick turnaround times, how we can think about better integrating systems so that there's actually simplified solutions for some of the additional requirements that we're driving into the world of systems. We also want to think about passenger experience. So as passengers, systems is the unique area which can really drive some significant aspects around passenger experience. All of us want to be very connected in our world today. So we all feel very isolated if we lose our data point, our data signal on our phones. We feel incredibly isolated on an aeroplane when we're told to turn into flight mode on aircraft. So what can be done in terms of improving some of that connectivity, not just in terms of on the aircraft, but probably in the whole transition of moving from the ground, getting on board, and then coming off the aeroplane afterwards. So a whole area of debate and discussion around some of that as well. And that's just one aspect of passenger experience. So the next thing that I was going to do was really move on to our key topic areas for systems and equipment. We've identified in the strategy that Simon described this morning, we've identified 3 key areas. So the first one is around, particularly around, sorry, I might have gone too many there, next generation systems and equipment. So we're going to expand on each of these in a moment. I'm going to give you a slide on each of those to explain what we mean by that. It's quite a collection of areas around the world of systems, but it brings with it some unique challenges. The second one is really around smart connectivity and data systems. So you'll hear a lot more about this as we go through, particularly on some of the panel discussion. You'll hear more about why connectivity, security, and data systems are so important for the future. And the third one is really thinking about autonomy. So all of those air vehicle concepts, and anybody who's been in the vehicles breakout session in one of the other rooms just recently, you'll have heard about all sorts of new concepts around vehicles, lots of air vehicles flying around. There are a finite number of pilots in the world today. There's probably not going to be that many more going forward. Are we all going to be qualified pilots? Are we all going to train to become expert pilots? Probably not. So the world of autonomy is going to be critical for releasing that market around some of those new smaller vehicles. So let's have a look at systems and equipment first of all. And so in this slide you can see I've just cherry-picked a few areas that we mention in our strategy. There are others as well, but these are just a few areas to really help you to think about it. So first of all, it's about lightweighting and high efficiency. And very much about high reliability. So we really, really want to push and continue to push on all of those factors. They are things that, from a commercial point of view, make a huge difference to our airframers. So how can we actually ensure that each of those, in turn, continue to be developed with some novel technology? Thermal management. Huge challenge, and you might hear thermal management mentioned in virtually every one of these panel sessions today, because there are different aspects of thermal management that really will dominate the success or viability of many of the future technologies and future products that we're looking at. So that it's not just about thermal management in terms of being able to dissipate heat, it's also about systems and materials which can deal with harsh environment. So in many cases, we want to be able to put things out there. We want to keep it really simple. We don't want to put in lots of heat exchangers. We don't want to put in lots of additional equipment. We want equipment that can survive in a harsh environment. It's a balance between the two things. It's a balance between adding more complexity in terms of heat management system to having a more arduous capability within your materials and technology. So some good challenges there in terms of things to think about. The third one is about systems integration and installation. So this is the unsung hero in reality of everything in the world of systems. So it's really, really critical. So everybody who's developing a technology in the world of systems, it only really has merit if you can really truly demonstrate it integrates successfully at platform level, and it integrates into that wider system in terms of the way that that vehicle is being used. So having that system and system of systems view in terms of how you integrate, how you physically install, how you functionally install that technology, absolutely critical. And that kind of know-how and capability, a particular strength, I should say, in the UK. We need even more of it going forward. We're adding more and more systems as time goes by, but integration and installation from a systems perspective, absolutely vital. And then we're also thinking about alternative fuels. We're thinking about what could that impact be on the rest of the systems world. Well, systems deal with fuel handling. They deal with fuel management. If we're thinking about some of these novel fuels that we've discussed in some of the sessions earlier, then that has some impact in terms of what we do with our fuel systems that we've got around us today. So we need to really think about that, because all of that has an impact at whole aircraft level as well. So certainly fuel handling is going to be probably a differentiator. So lots to think about in the world of systems, and you can see just examples there from our strategy around the world of systems and equipment. So moving on to our second one, which is about secure connectivity and systems leadership, data systems leadership, I should say. So I've put this together in a slightly different way, to which I'm sure you're going to hear from our panelists when they talk about connectivity. But basically, these are the kind of user requirements. So you want to be able to operate the aircraft. You want your flight crew to be able to communicate with the rest of the world so that it can actually safely operate that aeroplane. So you need secure communication in order to make that happen. We have some of that today. We have a lot of that today. We're going to need more of that going forward, and we're going to need to think about how that might play out going forward with more and more vehicles operating in very congested airspace. Second one is about cabin connectivity. So what does it look like? What does it feel like? Look like as passengers, as consumers in the air vehicle? You want lots of connectivity. We all want connectivity. We want lots of data. We're all data-hungry people. Our expectation has risen thanks to our smartphone people. We all love data, and we're incredibly hungry around media and all those kind of good things. Our third one is something slightly different. So there's lots of equipment on the aeroplane, which today is connected in many cases through wired systems, quite heavy wired systems. In some cases, some of those could benefit from wireless connections. That might be an area of interest. There's also, how can that equipment that's on the aeroplane, how can it download some of its own health capability to the operators of that equipment so that they know how that equipment is behaving. So that's just another aspect of connectivity that we want to bring out. And our fourth one, I can't even count today. Fourth one is all about cybersecurity. So two very simple words, but one very significant challenge. So this is really hard. There are lots of approaches. There is a well-developed approach for dealing with cybersecurity. It takes time, it takes effort, and it takes good process control in terms of the way that we deliver that. So really critical. So we've brought it out particularly for this. I think cybersecurity is one of those key areas to help us in the future around some of these more complex systems. So, and very much around integrated connectivity. I mean, that's probably the big message around that. We want integrated connectivity so that everything really links together. So, moving on to our third area, which was really around the world of autonomy. So you can think about autonomy in all sorts of different ways. And when we talk about autonomy, you could be thinking about autonomy in the factory environment. You could be thinking about all of those things. We're not really thinking about autonomy in a factory environment. We're thinking about autonomy in terms of the way that you operate the aeroplane. So that brings us back to my dilemma of how am I going to operate all of these new urban air mobility platforms and things like that when I've got a particular crisis around pilot availability and things like that. So this is about wanting to actually develop different strands around the world of autonomy. So one of those areas is around, certainly around ground handling and some of the checklist type operation that needs to be taking place on the ground. There is about the aircraft control and monitoring. So how do you actually operate the aeroplane? Is it done remotely? Do we have a remote operator driving, effectively monitoring a number of airborne platforms? Lots of different ways that this can be done. What about aircraft health management? It's going to be really critical if we've got an autonomous air vehicle to understand what the actual state of health is of that platform, so that we know what the actual next operations might be, or next realistic operations might be for that particular platform. And then the last one, again, these are all big challenges, but how do you integrate an autonomous air vehicle into the air traffic system? Quite a big challenge here, and it's not a challenge that's an immediate transition. This is a challenge that will happen over many decades. There will be lots and lots of conventionally piloted aircraft, as we know them today, still operating for many years, and we know that if we start to introduce autonomously controlled aircraft, they'll need to interact in that same airspace. So how do we deal with all of that? So some of that needs to get thought about as well. So autonomy is quite an exciting opportunity for us. It's an area that we've probably got, out of all the things that we're probably going to talk about today, it might well be the area that's the least well understood, certainly from a commercial aerospace point of view. Let's probe into that a little bit more in our panel session later. So, and my last slide before I hand over to and introduce our panellists for this afternoon is really just to show you, we did have a roadmap that Simon mentioned this morning. So there is a little roadmap that we put together, which is meant to be quite provocative. It's meant to show you a little bit around the world of systems. It really integrates all of those things that I've just talked about, so you can digest these at your leisure. When you pick up the document, you can download the document and really explore that. And we're looking for some healthy debate from all of the sector around each of these roadmaps in reality. So that was really my introduction to get things moving. So on to our panel. So this afternoon's panel is, I should have probably mentioned that I'm Mark Scully from the Aerospace Technology Institute, but I kind of know that. So our next panellist is Peter Alsop from GE Aviation. We then have Julia Jiggins from Tellus, UK. And we then have Alan Wake from BAE Systems. And each of them are going to deliver some very different aspects around the systems strategy that I've just talked about. So without any further ado, I'll hand over to Peter.
Thank you, Mark. We've got 5 minutes each just to tease out a couple of topics from this particular theme of systems. And I'm going to talk about systems and equipment, and I'm going to talk about it particularly from 2 points of view. One is how systems and equipment drive value, and the other is how systems and equipment can help the industry move forward. And I'll illustrate that with a couple of examples of ATI projects that are going on at the moment, one of which is next door. If you want to go and visit the team, they'd be delighted to see you today and tomorrow. So in terms of driving value, the systems and equipment sector is one area that can help constantly refresh opportunities, both with original equipment and in service. It's a broad sector, and you can imagine the sector operates from components to integrated systems, and from mechanical through electrical electronics and software. And some of those are brought together in unusual ways, whether it's controlling electromechanical items, whether it's integrating software, or providing a platform for functionality to work. And there have been a number of trends we've seen happen over the years. We've moved from an analog domain to a digital domain. We've moved from a series of federated closed systems to a network of open systems. So what does open mean in this context? It means that the system integration is easily understood and extendable, and that within the equipment itself there are known interfaces into which new functions can be provided. And actually that's one area where the sector has grown new market opportunities, in that all of a sudden people who have a great idea or a novel solution or algorithm can find a home for that equipment through the integrator without having to provide all the other infrastructure that might go with hosting some equipment on an aircraft. The other big trend we're seeing is to move from hydraulic, pneumatic and electrical to more and all electric. It's interesting as you think about it, when we first started thinking about all-electric platforms on integrated programs, we were talking about the 1 megawatt aircraft. And of course, what you heard this morning is that one of the propulsion systems on a hybrid electric demonstrator vehicle, the EFAN-X, will have a 2 megawatt engine motor to drive that fan in that location. So 4 of those, suddenly we're going from a very challenging all-electric solution of a 1 megawatt aircraft to suddenly, for maybe just a regional aircraft, looking at 10 plus megawatt solutions. So that just gives you a feel for where we were in terms of offtake from engines to serve systems and equipment need, to how we're going to deliver propulsion in the future. And then the other thing I just wanted to say, just to echo one of Mark's points, was that what's driven this, in terms of system evolution, has been benefits in the marketplace. So we don't just do things for the sake of it, we do it because it takes equipment weight off the aircraft, which can be payload, it can be passenger services, it can be an overall lighter solution. And we heard about sustainability as the theme during the day. And systems and equipment sector can help deliver sustainability in so many ways, whether it's making sure that there are optimal approaches to airports. So you'll be familiar with the idea that typically aircraft are very inefficiently driven to approach by what's called drive and dive. And by using continuous descent approach technology, you can take quite a lot out of the approach. And when we talk about the power of 1%, all the work that goes on in the other components of the aircraft, clever and creative changes to the way in which software is commanding and controlling systems can give you all those benefits and keep adding value through change. So in terms of moving forward, that sustainability just doesn't talk at an equipment level. It talks about how are we going to sustain and grow our workforce, the attractiveness as a marketplace for people to come and work. Our sustainability in terms of the affordability of our development processes and our manufacturing processes. And I'm sure many of you, when you're involved in specifying, developing new facilities, are thinking, how can we contribute to this being a net zero operation as we move forward? High-value design, not just cutting to exciting young people about being part of our industry today, but also continuing to position the UK and the systems and equipment sector to continue to deliver value to the overall aerospace problem. And I think that's one area where in the UK, a cross-sector initiative, which you heard described as Brunel, high-value design, the ISCF Challenge Fund, could be a way in which associated sectors such as defence and aerospace can have a framework to work together to drive value. Because quite often our sectors work out of cycle with each other. So when one sector is driving benefit and advancement, another one might be in a research phase and could pull through those benefits when it gets to a design activity. And then, of course, we're all very familiar with the idea of model-based system engineering. So what are we actually doing with what sometimes is called the digitization of engineering? How are we making sure that the information we're capturing in the field really is driving design decisions and helping us put through the change as soon as possible, whether that be an update through an in-service activity or a new solution. I think one thing about the journey we've been on, and we heard the Airbus Sitio this morning talk about looking back to 1969. We've been doing something very similar around GE, not really to think about, wasn't it wonderful in 1969, but to say 50 years ago, the industry was doing this, and we're now here. And the challenge I have is, what is it we're doing today that in 50 years' time, people will say, those folks who met in Birmingham in November 2019 really drove a change that's revolutionized the way we do aerospace today. One of those, as a joined-up industry activity we're doing, is the ATI high-class project, where we're looking at really tackling affordability into our software and system engineering processes, and also how we will leverage some of that commercial technology that Mark took out of his pocket to show us with his iPhone. It's fabulous, but it's not really suitable out of the box to help us continue to deliver the sacred trust of safety and the emerging threat of cybersecurity. And those are two initiatives we have to work on. Cybersecurity, both from a design process perspective and a physical product implementation perspective. I guess if I was to use what was a phrase we heard a lot of a few years ago, faster, better, cheaper, in this time it would be focused on how we can help deliver the urban air mobility solutions of the future. It was fascinating when you think about it. We heard this morning that we're moving potentially an air traffic world from thousands of transactions a day to millions of operations and transactions today. And that is a fantastic opportunity. And in this sector, we've been very successful at winning in global markets, mainly because we have to, because our integrators of our products and services are truly global in their footprint. So I would encourage you all to think about what can we do to bring some of the new technology to bear in 2019 to give us that 50-year look ahead to that exciting environment that was visualized on the front page of the new technology document from the Institute. Thank you very much.
Thank you very much, Peter. So our next panellist is Julia Jiggins from Tellus.
My son will be groaning. I've got technology. So smart connectivity, information management systems. Mark has generally very nicely put it into three categories. The industry today doesn't look at it as three categories of cockpit, cabin, equipment. We are talking about the Internet of the aircraft. You want data everywhere. You want the data to be able to be made into information. You want the information to be able to make decisions. And it is whether you want those decisions so that you have got a more comfortable passenger experience through lighting, temperature, connectivity if you want it. You want to have more efficient operations in the cockpit to make sure you're taking the most efficient flight, whether it's a 4D trajectory or making the maximum of what's coming down the pipe with regard to air traffic management. You've also got a whole aspect about operational efficiency. How do you make this very expensive asset as part of a wider network, and how do you get the most efficient operation so that you're not wasting it, particularly with weight, unnecessary flights, diversions, delays, the whole aspect. So you want to track this asset. So you have to think of this aircraft or urban air mobility or UAV as a node within a much wider ecosystem. And therefore connectivity, which is reliant, cyber-secured, is a major enabler to use that wider ecosystem. And so you're not talking about just connectivity of the traditional aircraft to the ground. We're talking now about mesh networking, aircraft talking to aircraft. We're talking about taking the latest availability of data links such as 5G, which can fundamentally change the way that data is moved on and off an aircraft, whether it is in the airport taxiing or in the air from an air-to-ground capability. And then all this is that you're generating, and that today airlines on the latest aircraft are generating a lot of data. What they're struggling with is how you convert that data into information and how that information is enabling them to make decisions that are effective and timely. So as we're going into this more open network, open system, we are having to bring in a different way of operating. So if you look at it, and we could have, the team in Tellus could have spent weeks putting more and more types of data. And this is not an exclusive list. It is the list that was this week's version of the list. But you've got to look at it. You've got cockpit data, you've got flight safety data, you've got aircraft data, you've got cargo data, you've got passenger data, you've got cabin data. And you can track now with the sensors anything on the aircraft. And the more sensor data is much more generating the volume than either a passenger with terms of voice or with us with a plane or an aircraft or an air vehicle communicating with the ground. So there's a lot of data being doing. But to enable you to use that data or the information to make decisions, you've got to bring in a lot of tools and processes of the digital world that are not common practice today. So you're looking at multiple bearers integration. Great having lots of data links. There is a limited space of putting antennas on the airframe. So we have to be more innovative about how you do that. We need to be able to do a lot of advanced data analytics. We need to be able to get data on and off the aircraft or the air vehicle, but we need to be able to do a lot of real-time data analytics with using AI, big data, and the whole process of digital tools to enable that to become information. We will, as you're going into more open network systems, multi-layered secure approaches. And was mentioned about high class, there's looking at the new skills and new techniques about how we can put digital trust or Security Operations Centre in the sky, SOC in the sky, to enable us to be able to be offering different layers of security of all this open network data. And you've got the other aspects of using tools and techniques and processes such as blockchain to help move that information. So there's going to be a lot of information. It is all segregated and managed depending on how you want to use it. It is only going to get bigger. And the point about this is that connectivity and cybersecurity is moving at a speed today that the airline industry or the aviation industry is not used to. The cycle time for updates is now 6 months to 2 years, not 2 years to 6 years. So we're looking at that pace of change and how we certify, how we prove and endorse the safety aspect of it is all critical. It is a very dynamic and changing part. It will only get more important as we go further down the autonomy path. Thank you very much.
Thank you very much, Julia. And on to our final panellist for today. It's Alan Wake from BAE Systems.
Hello, everybody. Alan Wake from BAE Systems. That's the air part of the business. So I'm actually a defence person, so it's a bit of a sort of sneaked in around the edge of an ATI conference. Following on from Mark's presentation and the presentation Victor gave us this morning, I'm going to be talking about autonomy in aerospace. What is it? Where can we make use of it? And some of the outstanding issues. So, change the slide. So first, what is autonomy? So if we look at the top left of the diagram, most of the aerospace systems today that we use are either manual or automatic. Autonomous systems actually perform tasks independently. They do that based upon perceived inputs and internal decisions that they make themselves. They've been used, obviously, in other domains other than aerospace for quite some time. Obviously, automotive are making big use of these systems now. But as yet, they're not common in aerospace. Most of that's around the problems to do with certifying and trusting their behaviour. If we look at the top right, autonomous systems can be categorised by the approach that we use. These vary in the level of determinism that's inherent in the system and also their ability to deal with emergent behaviour. So going from the right-hand side, artificial intelligence is rule-based. It uses first-order logic to make decisions. It's actually the most deterministic of those types of autonomy, but it can't actually deal with anything that it doesn't already have in its rule book. So it can't deal with emergent behavior that the programmers didn't originally think about. Machine learning, one in from there. It learns the relationships between input data and actions. It does that without specific programming. So neural networks are an example of machine learning. They can be trained how to relate certain inputs to certain conclusions. They're non-deterministic, so that gives us a bit of a problem, but they can learn to deal with emergent behavior that wasn't within the original data set that was generated to train them. Going right to the left, deep learning is sort of current state of the art. Convolutional neural networks are an example of that. That's a type of neural network that has multiple layers, so some of the layers are hidden within the system itself, and each of those layers can be focused on a different element of the problem. So it's a different level of abstraction as you go down through the system. They're very non-deterministic by the pure nature of them, but they can learn to deal with complex relationships between the inputs and the required outputs that you need. I think the thing to take from that is that all of those different types of approaches, and this is a fairly simple categorization of the types of approaches, both have advantages and disadvantages. That's through complexity, certification, and the trust that's inspired or can be taken from the system. So when we think about autonomy in aerospace, what do we usually think about? Well, most people think about sort of platforms that are going to come along in the future and using autonomy to fly those platforms around. Actually, that's a really hard problem to solve. The adoption of autonomy within aerospace is probably going to be a gradual process. So it's going to start with simple tasks, aids to the pilot, and that's going to be then evolved into more complex roles. So if you think about a platform today that's got 2 crew on it, the use of autonomy to allow that to go to single crew, the ability to have it remotely piloted in an emergency situation, and then eventually to an unmanned flight, you can see the sort of evolution through more complex stages to get to where we need to be. The thing, I guess, to take away, though, is that, as we've discussed through a number of the panel sessions so far, autonomy is sort of essential in order to open up the airspace that we need to do. So if you're thinking about things like urban air mobility, new ways of having agile airspace management where you can put more vehicles actually into the airspace, they're going to rely on these autonomy techniques in order to make them possible. However, going to the bottom of the diagram, autonomy doesn't just happen within the air vehicle. Mark's already mentioned ground handling and the use of it in airspace management, but actually it goes right through the life cycle. So in design and development, you can use autonomy to help you analyze the characteristics of the vehicle and design it more effectively. Manufacturing, the use of robotic manufacturing or cobotics, where the human operator is augmented by autonomy. Training, where you can actually tailor courses to specific students or the type of approach you want to take. And support and fleet management, where the big data issue comes in and you can use autonomy to sort of analyze the data. The bit across the bottom is actually trying to point to the fact that certification and trust is actually different across those life cycles. So that the problem is easier or harder depending on which of the life cycle phases you're in. I would say the most difficult one is when we're trying to apply it directly to the air vehicle technologies, and you get sort of a different problem set when you look at it across the other aspects. So, different approaches to implementation and different levels of trust required in the system are appropriate to those different life cycles. So, if we start thinking about implementation first, there's a problem which is highlighted by the graph on the right-hand side. As autonomy in the system, it's not easy to see because I've overlaid the graph twice, but as autonomy increases in the system, the requirement for trust in the system increases as well, because if you've got something that's a manual system, you inherently trust what you do with the system itself. As the system itself takes over more control, then you have the level of trust required goes up. But actually, because autonomy is increasing, the complexity of the system is actually getting greater as well. And as the complexity increases, our level of trust within the system inherently falls. So there's a dichotomy there between the nature of what we're trying to do. What we actually need to do is try and understand how we can affect the implementation of those systems in order to help us overcome that problem. So we need to consider segregation of elements, the use of partitioning between different elements in the system, potentially the use of probabilistic certification approaches around the certification of those autonomous bits of the system, and in early days, potentially only using autonomous systems in an advisory case rather than having to rely on the decisions that they make. Alongside the implementation issues, there's the question of how we define trust, and I know Victor talked about this in the plenary session quite a lot this morning, but is it really defined by, looking at the left-hand side, is it the provenance of the data, so we know where it's coming from, we can trust where it's coming from? Is it the fidelity of the data, that it fits within the boundaries we expect? Is it about predictability of the decision that it's making? Or is it about the simplicity or explainability of the system itself? Actually, in reality, it's a combination of all of those things and probably more things as well. So we actually need to come up with some sort of complex way of identifying what trust is in the system. It's a combination of all of those factors. Also, we need to not just have trust in the decisions the system makes, we actually need to have trust in the data that's flowing through the system as well, and there's slightly different between those two things. And it does lead to some difficult questions. So how do we set a required level of trust either in a decision or within a piece of data that's flowing through the system? What is a required level of trust for any one particular data item? How does trust flow through the system? So if you attach a trust level to a particular data item, how can that be transmitted through the system by the use of metadata? When you get to a system boundary, how do we represent trust there to the actual end user or an operator of a system? And if you've got a system that's made of modules, how do you transfer the trust that you've got within the system across those modular boundaries? So in summary, in order to take advantage of autonomy, we've got to understand which bits of autonomy work best for which parts of the life cycle we're trying to target. We also need to understand the constraints that are applied on the implementation of the system, given what we're trying to do. But really, we need to develop a model of trust that's generic enough so that systems can be built of trusted components and then composed together into a greater system. It's not just about the algorithms, which I guess most people think about when we think about autonomy. Autonomy is actually also an architectural issue, and we need to cover those architectural aspects just as much as we need to think about the algorithms themselves. The systems we build are becoming more integrated. We've already had that discussion, but actually we're driven towards the use of open architectures, and that's again causing us problems because open architectures means you've got boundaries in the system, and this concept of trust and how it flows across the boundaries become difficult. So certifiable autonomy actually requires us to have sort of a group collective decision about how we want to represent that trust, how we can then go on to certify the autonomous components within the system. So what's required? Well, consensus, cross-industry effort, I think, to sort of understand those problems and define them in a way that we can all agree, and have a shared model for trust within the system. That's it. Thank you.
Thank you very much, Alan, and thank you very much all our panellists. So we are running a little bit behind, it's fair to say. We have been flooded with lots of questions, so we're not going to get through all of the questions, but we will take care to try and find a way to respond to you with some of those answers to some of those questions, and we'll explore how we can do that in the future. I'm just going to pick up on 2 or 3 questions that we can just ask our panellists. So I'll start off with, I think, a question for Peter that we'll start with is around integrated health monitoring. And the question is, how likely or how far-reaching is integrated health monitoring likely to benefit the UK supply chain?
So I think there's lots and lots and lots of opportunities. So whether that's helping operators understand when they need to take an action to avoid an unplanned delay, whether that's building a better understanding of the behavior of a product in the field that you can use then to improve a solution that's offered to a customer, whether that's a better understanding of the way components work together. And in that is an opportunity to say, actually, if I optimize my solution and then either a solution that someone else has for a piece of equipment or a component, then by integrating those together, I get a better net effect than operating through, in a slightly different way, that the boundary issue Alan was talking about, where having to mesh together lots of things if there's a reduced complexity. So I think it's opportunity. I think it's using the information smartly to improve design and product implementation. And it's making sure, I think, that customers see improved services for which is something for which they will pay.
Thank you. Good. So moving on to, I think, a little question that Julia, it's a question around connectivity and entertainment. So, and I think you've alluded to some of this in your presentation actually, but let's just expose it a little bit more. What do you see as the main topics for the travelling passenger in terms of connectivity and entertainment?
If you look at today's model going forward, you have a distinct difference between what you'd have for long haul versus single or short haul, single aisle aircraft. There's a desire generally for a lot of people to bring their own devices. So from an entertainment perspective, quite a lot of that is preloaded before people fly on a short haul flight. But on a long haul flight, people like to have a selection and a screen that is in front of them to do that. They are looking a lot more, say, is on your experiences being more tailored to what your history is. So as a passenger, you have an identity, so people will know what you like to watch, whether it's documentaries, films, news products. And there's a lot more following what I would say is the Netflix tagging about what information you want, whether it's audiobooks, reading, or local stuff. So there's a lot about that, and also about bringing your own device. There is also a different use of connectivity from a passenger perspective. Generally, a lot of people want to use email, social sites, but they don't want to use voice. So in a tube, it's generally not wanting to have a conversation that's blaring down the cabin. So there's still not an assumption that you will do exactly what you do on the ground. It is more of a tailored approach to it. And it is with the latest connectivity, the cost is coming down significantly from a megabit type approach. And the utopia that is now being looked at is it's effectively seamless roaming from what you have in your day-to-day package. You just walk onto the plane and you don't have all this signing on and going on to a different network. It continues to evolve, and I would say you'll see most of the innovation is coming into that connectivity, that service delivery, and it affects also with the lighting, the seating. You know, one of the challenges at the moment is a lot of people are going and using Alexa, or they're talking in the house about selecting services. That's not seen to be something that would really, you want 350 people asking for their, you know, films to be started. So there's still something about being in a confined space.
Okay, thank you. So third question is for Alan. It's around the world of autonomy, and it's the world of pilotless aircraft and public perception. So how should we go about dealing with public perception of pilotless aircraft? And I guess that builds to a certain extent on some of the activities that have already taken place around pilotless aircraft.
Yeah, so I think where people see autonomy these days initially being applied is actually in drones. So it's in much smaller vehicles. And there's already a problem with public perception around that. So we've got to take the public with us on the journey, and part of that is by selecting the right use cases to apply the technology to first. So whether that's, I think it was discussed earlier on today, whether that's the use of drones for emergency medical supplies, so you've got something where the people get behind it, whether it's the use of autonomy to fly aircraft which are actually carrying cargo on predefined routes rather than just open airspace, to get the public perception going and getting a positive benefit first before you move to more general use of it. I think it's that taking people along with you, and I do think that we will see autonomous freight an initial use of the technology, certainly for large-scale platforms. When it comes to things like urban air mobility, I think the jury's still out on exactly how that's going to work. Initial platforms, I still think, probably will be piloted. Moving to the sort of Uber model of everything being autonomous seems like slightly further away at the moment.
Okay, thank you very much, Alan. So I think we're now pretty much out of time, but thank you very much for everybody for your questions, and thank you in particular to our panel who have certainly helped us significantly today. So thank you very much.